My name is Chris McGinty, and I'm going to provide a short lecture here on the use of unmanned aerial systems, or UAS, for the collection of natural resource data. I'd like to acknowledge the Quinney College Natural Resources Remote Sensing GIS Lab for the support to create this short lecture and certainly the work that is behind it. Just to kind of kick things off, it's always interesting to note that various researchers and scholars, land managers, landowners over the last 3 decades really have realized the power and abilities of remotely sensed imagery as really a tool that can provide information to manage and understand and really make the lands better that they're working on. And so I think it is fitting that Tueller in Journal of Range Management in 1989 noted that one could visualize range conservation as obtaining the majority of their required management information from remote sensing instruments within 20 years. And certainly he was not far off with between 1989 and certainly 2009. There was a great deal of advancement, including the launch of mini satellites, the development of sensors, and so on. So that being said, a few discussion points for today. We'll talk about some of our project goals, study areas, and regulations. We'll nip the regulation just a titch, not too much. Equipment and data collection methods, just some of the things that we use in the Remote Sensing GIS Lab. Data processing, some of our results, and just maybe looking forward. And certainly if you have questions, you can post those in the comments section of the video and we'll get to them as we can. So, project goals, study area, regulations. Some of our goals really focus around a couple of key areas. Our initial research question is really, can high-resolution imagery that we collect from UAS be used as a surrogate method for collecting detailed land cover field sample data? And by that I mean, can that data that we collect when we go out and fly UAS surpass, supplement, or even just replace overall what we would collect if we were sending out a ground crew to collect data from, say, transects or visual observation. The second question is really focused around using ultra high resolution imagery from UAS to inform land cover disturbance mapping. So can we look at the land cover using UAS and map and evaluate what's happening on the ground? So that is disturbances, treatments for you land managers, impacts and results. So that kind of gets into the idea of monitoring. So in addition to those two kind of overarching goals, we wanted to make sure that we could identify some strengths and drawbacks of using UAS. That is, what are some of the costs associated with UAS data collection for natural resources. We want to be able to provide data collection support to folks on the ground. So those folks that are going out in the field, we want to be able to present them with another tool that they can use to help fulfill their mission when they're on the ground and they're doing their data collection. Ideally, project budgets continue to shrink. We would like to reduce site time visit and streamline data collection process. Now that can be done to whatever degree, maybe not in its entirety necessarily, but we'd like to be able to streamline some processes and make it so we don't have to spend quite as much time out there collecting data in person in a very extensive manner. Providing a defendable photo record is a very important component. Streamlining rangeland data collection processes overall, that is, looking at what we can get that would be similar or would mimic a transect that would be put down by a ground collection crew. And then just identifying other usable data products that the UAS might capture that we may not or have not understood thus far. So there in the right, the picture, we fly a couple different drones that we can talk about here in just a minute. There's an older Phantom 2, which we no longer fly, but each one of our drones has a name and a designation. So there's Parrot Head and Casper, two of our drones. Parrot Head is an S1000 manufactured by DJI. So we have a few study areas that we focused on for some of this initial data. Providence Canyon, Utah, and we are located in northern Utah, so we focus in on Utah areas. Millville, Utah is kind of our ag location. We look at a common garden. It's kind of a control area. Orderville, Utah is a different type of environment in the on the Colorado Plateau in south central Utah. And then Green Canyon is kind of a steeper canyon area with sagebrush and junipers that is managed by the United States Forest Service. So just as an example of one of our other areas that's kind of a little higher altitude elevation, than these other sites is the Sage Creek allotment in Rich County, Utah. It's kind of a sagebrush, sage steppe area that's managed by the BLM and NRCS. And we're working in that area to help support the ranchers who are really working on improving their overall forage capacity for these grazing allotments. So some of our equipment, generally our heavy lift machines are DJI S1000 Premium Plus systems. They're all registered with the FAA as required. They're multi-copter with 500 watt electric motors. There's 8 motors on the octocopter, of course, and they have about a meter wingspan, if you will. These are no longer manufactured. You can still get them because they're highly reliable. People really like flying them. They're a bit more manual than some of the newer models, like the M600, which DJI has used to replace this particular model. 11 kilogram max takeoff weight, so that's about 24 pounds. 21,000 milliamp hour battery. It's a 6-cell battery. And fully loaded, we get maybe 20 minutes of flight time, and so there's one of your limitations right there. And it's flying the A2 autopilot system, the 900 megahertz ground link control system right to the computer laptop. The gear on the landing gear folds up to the sides, and then you can see the camera. This is a Canon that has to be mounted here, but we now regularly fly Sony A7R, which is about 3 pounds lighter. But the gear pull up, so you have a full 360 degree view with that gimbal that you can see in the picture. The Canon that we do fly or did fly, we haven't flown it for some time now, just because it is so heavy, was a 5D Mark III. Fantastic camera, mounted to a ZenMoose 5D3 electronic gimbal. However, we've built a couple of other mounts. One for a FLIR A65SC thermal camera, some multispectral sensors, and then the Sony A7R, which is a 36.4 megapixel full frame sensor that just does a fabulous job of capturing data. Additionally, some of the other equipment that we use, because these are older UAS, we'll just use Fatuba 14SG transmitters. Fantastic transmitters used by RC pilots. It's a 14 channel fully programmable. You can see the picture there on the right, so you've got a button for just about everything and good menu control. This links in with DJI Ground Station. Now I'll say that, but as of lately, because of updates to Google Earth and DJI no longer supporting it, we've moved over to using UGCS as our ground control, mission planning, and general flight software. It has a similar feel to the DJI Ground Station, although I would say it's more well put together and certainly more functional. So that UGCS is really a nice system that we can generate our flight plans in and then fly our mission plans. Our ground control point collection. So this is an important point. We do ground control for all of our flights. We do real-time submeter accuracy, or we can tie into a local survey network and have centimeter accuracy X, Y, and Z components as necessary. And those are all collected on photo identifiable targets, which happen to be high-tech bucket lids from your local hardware store with numbers painted on them and a white dot in the middle. So nothing too terribly expensive in that area. Some of our methodology, just to kind of give you an idea for those of you that do or do not yet or are just getting into using UAS. Flying a big UAS or even small UAS requires the use of checklists to make sure that everything is appropriately tightened, turned on, lens caps removed, batteries charged, flight plans engaged, so on and so forth. So you really need to make sure that you have some sort of a pre and post flight checklist. We even have a in-flight checklist that we use prior to landing, and it doesn't have to be significant or long in duration to complete, but we do make sure that we don't leave our lens cap on, for instance, when we send a drone up for a mission. We always make sure that we evaluate our flight area carefully, check for airports and other restrictions. As far as our remote sensing GIS lab is concerned, we fly strictly under Part 107, and so that gives us opportunity to do a little more than you would normally do as just flying under something like as a hobbyist. And I shouldn't say it gives us more opportunity to do it, it just allows us to do it in a correct method. So talking to the proper authorities in the area, making sure that we're filing flight plans if necessary, and all of the various obstacle avoidance, area avoidance that we need to account for. Before we ever hit the field, we do an assessment of the area using aerial photography and develop a flight plan. We program our mission altitude and our operating envelopes, so what area we're going to fly in, identify areas where we might have some issues. Now this can all change once you get on the ground, but the UGCS software allows us to really put in some high resolution elevation data, LiDAR for instance, or other DEMs that allow us to really hone in on the area and create a nice flight plan. We save that and then certainly load it up into the UAS prior to flight. We distribute our ground control targets. As I mentioned, these are bucket lids. They're orange with black numbers painted on them and a white dot in the middle. This has been found to be very visible. Even in near-infrared data collection, we can see those. Not quite as well. They do not work for thermal data. For thermal data, we use a sheet of insulated silver bubble wrap with a number taped on it with a black duct tape. And that seems to work very good because of the thermal differentiation. We always conduct our pre-flight site and aircraft check. Of course, there's the checklist, as I mentioned. We look at for alternate flight plans in case of emergency, then complete that checklist and initiate the flight plan. So a lot goes into this. It's not unlike flying a regular manned aircraft in the sense that you have a lot of checks that you go through before you actually get into the air. So data processing. Data processing is generally all done in Pix4D Mapper. Pix4D has proven to us to be a superior product to others. We've certainly tested the other available, at least commercially available softwares on the market, and Pix4D tends to do the best job. We don't necessarily use the mission planner for Pix4D unless we're flying the smaller DJIs like the Phantom 4 Pro or the Mavic Pro or Pro 2. In that case, we will sometimes use the Pix4D mission planner. However, you don't have the ability to really adjust for the terrain in that software, and so we need to make sure that we can do that in some of the steep canyon areas that we work. So Pix4D Mapper requires photos, the camera and lens specifications, geolocation data, so your GPS data, and processing time. A lot of the drones will automatically geotag your photos. Our S1000s do not automatically geotag, and so that's something that we have to take into account, and we geotag them after the fact by mounting a small data logger GPS on top, and we only have to get them within a reasonable distance of where they really are in the real world. and then we'll use our ground control targets to tie it in nice and tight. So a few results of what we get with the UAS. This example is flown at 80 meters above ground level, provided a 2 centimeter pixel resolution. The flight time was about 18 minutes and it took about 10 hours to process, 2 hours of human interaction. Really didn't need 2 hours of human interaction, but we had some issues there with our ground control targets being a little hard to spot, and so took us a little extra time. And the 10-hour processing time can be taken down with a much a more robust processing platform. Here's kind of an oblique view. So using Pix4D, you can create the digital terrain model. Notice this is not LiDAR. This is just your standard structure from motion product. But what you need to realize is, as good as this is, you're not getting multiple returns like you would with LiDAR. You're also missing areas or have data gaps underneath canopy and trees where the sensor couldn't see. So you'll see those black holes underneath the point cloud, and that's certainly something that is a drawback and you need to realize. Again, just another vegetation structure. This test area in particular is in very steep terrain, very steep canyons, and we wanted to see how the S1000 or the various drones would handle in an environment where there was a limited field of view to the sky and GPS. The next site where we've done test flights extensively is our Millville site. This is a common USDA garden on Utah State University property near the Predator Research Facility in Millville in Cache Valley, Utah. This is flown at 80 meters again, so we have a 2 centimeter pixel resolution, about 13 minutes, but we were able to collect quite a bit of data because we didn't have any satellite visibility issues. This is all flat, open valley bottom. So 12 hours of processing time, roughly, and 2 hours of human interaction or so. Not again. There was some learning curve, but something like this at this point has been well winnowed down. Although there is some additional human interaction if you want to clip this out and make the data look a little neater. And just kind of zooming in, you kind of get the idea. You can see the cow in the lower right of the picture, the vehicle in the middle, and we zoom in a little further. The plants come into view, and certainly even further you can start to see individual parts of the plants as they appear on the ground. Alright, so third site is Green Canyon, Utah. This is a 1 centimeter orthophoto shown in 3D, and you can see that this is flown at 40 meters, so quite a bit less than the other, 40 meters less than the previous example. This is about a 28-minute flight time, so this was 2 flights and it took about 16 hours. We were really trying to hone in on some good extra detail from the area. And lastly, our site in southern Utah. This was an example showing some work being done with ranchers and land managers, showing the benefits of drones and UAS with respect to how their land could be managed and monitored. So this is the Orderville site. Then there again is one of our bucket lids. You kind of get an idea of what these look like with respect to a 40 meter above ground level flight. And finally, the last site in Rich County that we'll talk about. This has been put together in support of the NRCS, BLM, and the land managers, ranchers that use the allotments in the area. And the overall goal of this was to really identify what could be used, what products from a UAS would be most useful and usable with respect to monitoring and improving forage and land cover. So they're trying to improve the overall forage and land cover for their cattle. Also, the local wildlife is a critical component of this area because of hunting and other economic benefits. And so this is a key area for them to really focus on improving. And this is just nearby. This is another area where the local rancher is looking at improving the overall riparian area. This riparian area is fairly well hammered. It's been really worked over by the cows that have been there in the summer, and what they'd like to see this do. In this case, it's very beneficial if in these higher mountain valleys, when these streams become deeper and narrower, rather than kind of beat down with hoof prints and whatnot from the cattle. So over time, they want to measure this and see if there's general changes in the area. And there again, you can see the differentiation between the best available free data, so the NAPE data on the bottom, which is an absolutely amazing product for every single state in the union here, but certainly not something that would do the job for evaluating or monitoring this stream network. And there again, you can see the ground control marked by the bucket lid. Important note here is that you always want that white dot in the middle with the black around it, because you can really identify that in just about every picture. You can see those pixels that are white in contrast to that dark very well. And there again is just to zoom in, and this is looking at about 2.5 millimeter GSD or resolution per pixel. So with that, the overall summation of the work that we've done is several fold. I don't have a lot of the results shown here, although they're in some other presentations that you can find on YouTube. Generally speaking, we have found that using UAS as a platform to augment and in some cases supplement, but not necessarily replace ground-based data, certainly are out there. Now, there are some things such as percent area of a species from a planar view, or looking at just identifying species on the ground where the UAS does a fine job. Also measuring height of vegetation species, and I'm speaking of substantial species that are at least have a thicker canopy. Individual grasses not so much, but a tuft of grass, or certainly a sagebrush or juniper tree or something like that, you can really get a good elevation measurement from it. And so what we ultimately have concluded, and we'll certainly be publishing some of this information in the near future, is that a lot of this data can supplement what's collected on the ground, but really shouldn't be considered a replacement at this point. Use of LiDAR, multispectral sensors, and other types of remote sensing equipment will probably eventually allow you to get further down that road. But with just an RGB, a true color camera, you're kind of limited in what you can do. You can do some fantastic work, but certainly there's still some limitations, and you have to make sure that you're cautious in the overall results that are being promised, and what those results can be used for. But as a monitoring tool and as a quick assessment tool and collecting some basic metrics for land cover evaluation and monitoring, this is a fantastic tool in the toolbox. So with that, please feel free to reach out with questions. You can put them in the comments. We'll address them as we can, and we'll be continuing to develop our program further, and certainly publishing some other additional materials that relate to basics of using UAS, and in the future there will be some videos posted here that will just kind of identify some of those key components that we were able to derive from this data. So thank you, and please do reach out if you have questions.